Hi everyone, this is coming to you from Education for All. We are still looking at infinitesimal calculus. This is our second video. The first one was a bit long, about 24 minutes, not quite sure. We'll try to make this one short, not to go beyond 10 minutes. But then, to get the benefit of this one, you have to go and watch the first video first. We're doing like a series. First, watch the first one, second one, third one is coming, and probably a fourth one is coming. Because this topic, calculus, as we normally call it, its proper name is infinitesimal calculus. We explained that in the first video, and also explain the applications of calculus into various fields like physics, chemistry, biology, engineering, economics. We explain all that. So we are not going into that on this video here. What you see here on the board, I could have just put dotted lines, all planets take an orbital revolution around the sun. The planets, they revolve around the sun when normally they say the sun is the center of the planet, of the solar system. It's not quite right. They take this elliptical movement. This is the planet Earth. It's not going in a circular form as you see here, like this is the sun, then it's going like this. No, the sun is at the center, then the planets go around the sun in a circular form. It doesn't like that. They go in an elliptical form. So what does that mean to us? Anything that is elliptical, it means they have two axes. They have the major axis and the minor axis. What does that mean to us? It means when the planet is around here, is close to the sun, its speed increases. It's fastest. Any planet, when it's closer to the sun, its speed increases. But when it is a little bit further away from the sun, as the Earth is here, on this is the sun here, is farther here than here. So here, its speed reduces. Here, its speed increases. When it comes all the way here, its speed starts to reduce until it reaches at the maximum point of the major axis. So how does this relate to calculus? We know in the 1660s, Isaac Newton and Gottfried Leibniz, English physicist and a German physicist or German mathematicians, these people actually invented calculus. But they did it independently, but simultaneously. And even there was an argument between them, each one claiming to be the founder of calculus. But anyway, we are not going into that. But how comes now when we say calculus, we are talking about Newton and not Gottfried Leibniz? That is another topic. So, in the 1660s, Isaac Newton was not even trying to invent calculus. Instead, he was trying to understand motion. He was trying to understand motion in the 1660s or 17th century. Isaac Newton, he was not actually trying to invent calculus, what calculus is. He was just trying to understand the motion of the planets. That's all. Why this planet, when it moves away from the sun, its speed reduces. But when it comes closer to the sun, its speed increases. This is the kind of thing he was trying to understand. What is happening? How does distance affect He already understand gravity is involved. He already done some studies at that time about gravity. So he knew gravity is involved. So then he was asking, how does distance affect gravity? How does gravity change over time? And since gravity is changing with respect to position and time, by how much does gravity change over distance? So he was very much interested by how much gravity change over distance. He formulated his universal law of gravitation, which states that every object, every object attracts each other with a force which is directly proportional to their masses, the masses of the two objects, the product of the masses of the two objects, from and inversely proportional to the square of their distance, the square of the distance between them. That is, if this is Earth, let's say this is the Sun. So the masses of these two, the product of the masses of these two, the force of gravitation, according to Newton, is proportional to the product of these two and inversely proportional to the distance. If you take the centers, they are centers, that's square of the distance between them. So that is the law he formulated. That's what you see here. F is inversely proportional to 1 over r square. But when you solve this one, you put it in a mathematical form, you will get F, which is the force of gravity, is equal to this gravitational constant, and this is the mass of the one planet, this is the mass of another planet, or it could even be between me and you, and this is the distance between us, the square of the distance between us. Yeah. So if you plot this relationship between force and distance, the force of attraction here is slower, but here is greater. So when you plot that force of gravity and the distance, you get a graph like this graph, because the force, this relationship is changing at every single point. It's changing, it keeps changing, right? In order for you to understand what this graph means, let's take, for instance, this graph here. This is the graph of a line, a straight line. What that means, like demand in economics, demand and supply. Yes, demand and supply. When the demand goes high, supply goes high. So you get this kind of graph. When one thing goes up, the other one goes up at the same time. So that kind of relationship will always get a straight line graph. So here, if you want to measure the steepness, that is the gradient of this graph, because here we are looking at gradients now, but we shall come to that. You will see that if you take any 2 points, this point and this point here, you calculate the gradients between these 2 points. The gradient is m, so m here is equals to the rise over the run. The rise, that is from this point to this point, the distance between them, and also from this point now to this point, the distance between them. So the rise over the run, this minus this over this minus this, you get the gradient. And this gradient, if you take these other 2 points here, you find the gradient, the answer you get here will be the same as the answer you get here. If you choose other set of points, this one and this one, and again you find the gradient, that answer you get will be the same as the one you get previously. So the gradient is constant on this graph. As long as you are able to take 2 points, you will get the gradient. It's constant. But when you come to this graph, this is not a straight line. You cannot get gradient here directly. The only way you can be able to get a gradient here is you look at a point, like here, this point here, you draw a straight line. Yeah? And you need 2 points, but here only you have 1 point. So, which means you are in fact going to calculate the gradient of the tangent. This line is a tangent. A tangent is a line that just touches a graph or point at a single point. So when you want to calculate this gradient, you are in fact going to calculate the gradient of this tangent, this straight line, because it has to be a straight line. You cannot calculate gradient with 1 point. You need 2 points. Right? Oh, already gone 10 minutes. So Newton was faced with this problem. This was a big problem for him. This thing is not, when he plotted it, the movement of the planet around the sun, it doesn't get a straight line like this. This could have been very easy to solve, very easy. But when it takes this kind of graph, now it's a big problem. How is he gonna calculate the gradients? Because the whole thing about calculus, where we want to calculate things that happen instantly. It's like if you are calculating speed, for example, or velocity, you want to calculate the instant velocity or the instant speed. And what that means, that is what happens at this particular instant here. That is what you want to get. Newton encountered this huge problem. It was a big problem. And what did he do to overcome this problem? He thought, okay, I might not be able to get the gradient of this graph since it keeps changing at every single point. It's changing. But he's going to devise something. That is what unlocks infinitesimal calculus. He said, look at this circle here. Imagine now, this line, come on, just touches this circle here. He wants to find the gradient here. For you to understand where this is coming from, let's take for instance, you are driving your car and you are looking at your speedometer, the speedometer of your car. You know, it displays the speed you are driving at. So sometimes you see you are driving, you see your car displays 25 miles per hour or 25 kilometers per minute, something like that, where we are using miles. You see 25 miles per hour. That number you see on your screen of your speedometer, that 25 kilometers, 25 miles per hour, is just an estimate. It's never correct. It's just an estimate. It's not correct, because that is the problem Newton encountered. He wants to find instantaneous results, not average results. When you see speed is distance divided by time. This is, let me just say, average speed. It's distance divided by time. That is, you move from one point to the other point, then the time you take from that point to the other point. Let's say you cover a distance of 50 miles in 10 minutes. Just estimate. Yeah? So what is your average speed? This will cancel, this will cancel. So your average speed is 5 miles per hour. I put per minute. I put minutes here, so let me put it minutes per minute, yeah? That is your average speed. is 5 miles per minute. Every 5 miles, you do 5 miles per minute. You cover 1 minute. Every 5 miles, you cover 1 minute. That is what it means. Right? So, now, what this is telling us, let me remove this one. This 5 miles per minute is telling us that you move from point A to point B, and this is your 50 miles. This is your 50 miles. Yeah, from this point to this point. It's 50 miles. And the whole journey takes you 10 minutes. I know it's an exaggeration. I'm just trying to explain things here. It takes you 10 minutes. These 10 minutes you have taken to cover these 50 miles is from A to point B, from point A to point B. Right? But what was your average speed between this A to here? What was your average speed? And what was your average speed from A to this point here? See another point here. Maybe you stop somewhere to buy gas, put petrol in your car, or you stop to buy food on the way, enter a restaurant, take some rest. So you can see that what you get here is the average speed for the whole distance you've covered. But what was your average speed between this point and this point? Between this point and this point, you don't know it. You don't know. So that reflects this graph because the average speed changes. Here again, your average speed changes. So what you get here is your entire average speed for the entire distance you've covered. But you don't know the average speed when you stop to buy food on the way. It's not in the calculation here. Right? And having said that, now when you want to take the instantaneous speed now, instantaneous speed, that is, you want to take the instantaneous speed at a particular point, which is what Newton was concerned about. That was his problem, because it has to be that way to do certain things. Like without it, it wouldn't have been possible to send astronauts to space, because they have to calculate the G forces. Otherwise, they perish on their way going, even before reaching the destination. And also for whatever they launch, all these satellites, for them to be able to reach where they want them to go, they have to know about this instantaneous speed we are talking about. So now we're talking about what happened, the speed at this particular point. So the speed at that particular point, what is it? Is zero. When your car is running at a particular point, that particular point, your speed is what? Is zero. And what is the time there? The time is also zero. Instantaneous speed. So 0 divided by 0 is what? If you put it on a calculator, you don't get an answer. It will say error. This is actually infinity, we say. You see that? 0 over 0. At that time, even at that time, calculators were not able to, mathematicians were not able to handle this 0 over 0 at that time, because this infinity came later on. When you divide 0 by 0, your distance, the distance you've covered, you come all the way from this point all the way here. You want this distance here. What is the distance here? It's nothing. Where you stop here. And what is the time here? Time is nothing. So it's 0 over 0. This is what you get here. For now, nowadays we say infinity. But at that time, 16th century, there was no answer to this. Yeah. So Newton said, okay, I will do something. Let me sip my tea. This is going too long. Okay, I stop here and then do another video. Yeah. I stop here so that it's 20 minutes now.